Okay, good evening. Welcome back. Welcome to this last lecture, unfortunately. On the other hand, think about all the things you have learned during one semester. It's quite a lot. So yesterday on Monday, I just finished preparing the notes. The lecture notes now have an index. We have seen quite a lot of things, if you think about it. Two things that I'm recording on. Yes, evaluation. Let me just remind you, you have to fill some form on TACT website. Don't forget to do it. It's important. So you probably have to do it for all your courses. So today I have to finish the subject. So we have still some nice things to see. Let me remind you, we have seen the definition of self-adjoint. So we have a linear operator. It's a domain, a subspace, a dense subspace in H.
One word. There's no survey on that.
There is no survey. Nobody has found any survey for this course.
No, I just checked.
I found.
Okay, so if there is any problem, please send me a message. So we have a dense subspace of the Hilbert space, a linear map on it. The notion of self-adjoint means that the adjoint which we have defined is equal to the operator itself. It implies this equality, but let me emphasize it once again. This equality is not the definition of self-adjointness. This is a definition of symmetric, but there are more symmetric operators than self-adjoint operators, so it's a larger family. We have also seen what is invertible. An operator is invertible if the kernel is 0. It contains only 0. But then the inverse is defined on the range of the initial operator, and you come back to the domain. Now, if the range is the entire Hilbert space, it turns out that the inverse is a bounded operator. In this case, we say that A is boundedly invertible because it has a bounded inverse. The resolvent set, it's a subset of the complex plane. It's a set of Z complex numbers such that A minus Z times identity is invertible. So it means, and it's invertible in B of H. So it means first that it has no kernel, it's injective. And in addition, its inverse is bounded. So we are exactly in this case, where the range is the entire Hilbert space, which means this is bounded. If you think about it, it's an open set. You can check that it is an open set by using the Neumann series. So when we take the complement, if we take the complement in C of an open set, the complement is closed by definition, and we call it the spectrum. And this is a right notion which generalizes a set of eigenvalues. So for matrix, we only have eigenvalues, but for operators in a Hilbert space of dimension infinity, this is a right notion which generalizes eigenvalues. And I recall, so this is a definition, the complement of the resolvent set, but you can also observe that it is a set of Z such that either this kernel is not 0, in this case it's not invertible, or it is 0, the kernel is 0, which means that it is invertible, but the inverse is not bounded, which contradicts that the inverse is bounded. So this is a complement. And I ask Hevido to prove the following lemma, or to work on this example. Take H, L2 of Rn, a multiplication operators with a continuous unbounded function. You can take more general function, but this is the simplest case, bounded and continuous. Then the spectrum of this multiplication operator is, I'm not sure if I wrote it correctly last week or if I did a mistake. It is the image of Rn by phi. So if I write it, it is a set of phi of x for any x in Rn. But be careful, you need to take the closure. So because it can be a set which is not closed, it takes the closure. And this is why last time you asked me why the spectrum of the multiplication operator given by the hyperbolic tangent is closed interval -1, 1. It's precisely because you need to take the closure. Otherwise, you would have open interval -1, 1. So by definition, the spectrum is always closed, yes. But this set without the closure can be not closed. For example, the image of R by the hyperbolic tangent is -1,1 open, but the spectrum is a closed set, so you have to take the closure. Set of eigenvalues, this is what you know, it's a complex number such that you have an element in the domain of A, which is not 0, and AF is ZF, like for matrix. And if we collect all eigenvalues, we denote by sigma P of A, the point spectrum of A is a set of eigenvalues. It is inside the spectrum. Why? Because for an eigenvalue, this condition is indeed, it's not 0, because you have exactly this eigenfunction in the kernel. Now, a very important theorem for quantum mechanics or for self-adjoint operators in general is that the spectrum is always real, like Hermitian matrices that have eigenvalues which are real. And I just added one more sentence. If you take two eigenfunctions associated with two different eigenvalues, they are orthogonal. This is also true for matrices, but this is also true for in this more general framework. I put the proof of this theorem in the notes. If you have some time, please have a look at it. It's an important result, and you can understand the proof. And then I wanted to present three types of operators. So I just did the first one, and I'm going to continue with the second and third one. I already spoke a lot about multiplication operators in Rn. Now I don't want to consider only continuous and bounded functions. So I take any function from Rn to R. I take R and not C because I want to consider self-adjoint operators. And it is one exercise to show that it's going to be self-adjoint if you take real value. And I'm just assume that it's measurable, so it's very general. Now, there are different notations for multiplication operators. Either, do you have any question? Can you turn off your microphone? Please, your microphone is on. I'm muted. Okay, so there are different notations for multiplication operators, either M phi, which is the one I use, or phi of X or phi of Q. This is more from the physicist. I recall how it acts. Now, I define a domain. The domain is a set of F in the Hilbert space, so that this M phi on F is also L2. This is the largest domain, and it turns out that if you have a real function and you use this domain, the operator M phi with this domain D of M phi, this is self-adjoint as soon as phi is real valued. An example, take just phi of X is multiplication by one variable, xj. This satisfies everything, it's real. You can define its domain, or take, this is more important, this function, which is 1 plus x squared. So this is x1 squared plus x2 squared plus x3 squared, and so on. Take power s over 2. And quite often we use this notation. It's a bracket. It's called Japanese bracket for this function. This is a definition. And then you look at the domain. We define it, and it turns out that the domain has also a specific name and a specific notation. It's called H with the index S of Rn. This is just the domain of this function, and you can check what it is. It's called a weighted Hilbert space. Okay, this is just for information. Last time I started to speak about differential operators because they are also important. Let me just start again. I will probably change a little bit the point of view. So this is a second example, differential operators. Of course, you can interrupt me at any time, except that I want to finish. So if you interrupt me too many times, we will finish after 8. So the one who asks too many questions will be blamed by all the other ones. How to define I want to define this minus I dj for f in L2 of Rn. So this is derivative with respect to the j variable, and for some reason we multiply by minus I. Okay. It's clearly it's going to be a linear operator, because if you take a linear combination, the derivative is a linear action. So it's a linear map, but the question is how to define more precisely the domain of this operator. The domain of this, by definition, it should be the set of f in, let me just call it this H for simplicity, but it is L2 of Rn, the set of f in H such that minus I dj f is again in H. This is by definition the domain on which you can define this operator. But what is the meaning of this? Of course, if you take f smooth, you know the meaning. But I want to have the most general f. So it means, how can I define a derivative such that when you take this derivative, it's not even continuous, it's only L2. So this is not completely trivial. So there is a slightly different approach which uses Fourier transform. And so I want to give a meaning to this. So recall the Fourier transform. It's from L2 of R. I already mentioned this. It is a unitary map from L2 of Rn to L2 of Rn, unitary, and we know what is the meaning of unitary. I introduced it 2 weeks ago, and it acts on L1 of Rn. Remember the formula I want to give, and you know this formula. I cannot write it for all f in L2. I need to define it on something slightly smaller. And what is the formula that you should know for Fourier transform? The Fourier transform of f at xi, there is a constant which depends to pi power n over 2. Integral e minus I psi times x f of x dx. And we integrate on Rn, when psi is any element of Rn. So this is the definition of the Fourier transform. Why I take it on a slightly smaller domain? Because look, if you take only it on L2, how do you define this integral? It's a little bit a problem. It's possible, but you have to be careful. You have to do it as a limit. It's an improper integral. While if you are in L1, it's not an improper integral because it's absolutely convergent. That's the point. So in L2, it's an improper integral. Okay, this is the notion of Fourier transform, but we know, or I already said, it extends from this set to a unitary map from L2 of Rn to L2 of Rn. And we have seen one more thing. By the way, there are many exercises now on the website. I'm quite happy with many of them, or with all of them. If you have time, again, during the summer, if it is raining, just go through some of them. You can learn something. And you can, they will stay on this website, so you can always come back. How can I use the Fourier transform? So I recall for f in the Schwarz space, we have seen this equality. It was easy to prove just by integration by parts. F is equal to xj. So what it means, taking the Fourier transform of a derivative is the same as multiplying by xj the Fourier transform of f. You can check this, and there is a report about this. So now look, I want to use this because this is what I would like to have. And I have something of this type here, which means I can give a meaning to this if, so this is in L2 of Rn, if what? If the right-hand side is also in L2. So if this is in L2 of Rn. But what does it mean? It means that F applied to F is in the domain of this. So this is equivalent to F, the Fourier transform of F belongs to the domain of Xj. Think about it. I want this to be in L2. Then this Fourier transform doesn't change anything because if it is in L2, Fourier transform is again in L2. So I can forget it for a second. But this guy is going to be in L2 if the right-hand side is in L2. And the right-hand side is in L2 if this is in the domain of Xj. So I end up with this conclusion that minus I djf is in L2 if Fourier transform of F is in the domain of Xj, right? And in fact, it's a if and only if. You can go in both directions. Okay, but then how you can finish the argument? Now, so this is equivalent. This, in fact, I can put an equivalent. Oh yeah, in your report, always think about something. When you write something, some lines, you should say if these two lines are equivalent or if there is an implication. The reader should not be obliged to guess. You should tell from line 1 to line 2, it's an implication or it's an equivalence. It's important to say it because it makes a big difference. So always remember the reader should be able to follow without guessing what you are writing. Okay, so let's say this guy is in L2 if Fourier transform of F is in this, but look, this last condition is equivalent to F is in F star of D of Xj. Just take this equality and multiply by F star, so the adjoint. It's going to give you F star F, which is just identity, it's unitary. So F star F, which means F, is in F star of Dj. So we have it now. This guy is in the domain of H if F is in the image by inverse Fourier transform of the domain of Xj. And the domain of Xj is something quite simple. You need an integral to be finite. So conclusion. The operator minus I dj with the domain Fourier transform of inverse Fourier transform of Xj is a self-adjoint operator. So please think about, this is a quite nice result because it tells us how to find a domain for this operator, which is clearly a linear operator, but it's not so clear what is the domain. And now you can do the same thing. Similarly, if you take alpha, any multi-index, we have that minus I power alpha, minus I define this, you take the partial derivative power alpha j. With the domain Fourier inverse of domain, Fourier inverse of the domain of the multiplication operator x alpha, And again, this is easy. The domain of this one is a set of f such that when you multiply by this polynomial, it is still L2. Again, is self-adjoint. Do you have any question? I told you this is a quite powerful tool. And I can do one more step because you probably know the Laplacian, and I put minus. What is minus Laplacian? It is d1 square plus d2 square plus d3 square plus dn square. The minus has disappeared. Some people define Laplacian already with a minus sign. It depends. This is called the Laplace operator. Then what is the domain? So we would like to define minus Laplacian on a domain. What is the natural domain of Laplacian or minus Laplacian? It doesn't, the domain, it doesn't see the minus sign. Think about it. No. Minus Laplacian, I will repeat what you said just before. F star of x square, which means x1 square plus x2 square plus x3 square and so on, which is much bigger, so it contains indeed C2. This has almost no meaning in this context because you don't need two derivatives to be in L2. Or no, it's not even this because a C2 function is not always in L2. So please forget this. And by the way, minus Laplacian, Fourier transform, bless you, H2 of is it still on the blackboard? No, what is this HS? Remember, HS is a domain. It was here. It's a domain of the operator 1 plus x squared s over 2. And what I'm claiming is that this one doesn't play any role because at infinity, the function x squared or the function 1 plus x squared, they behave exactly the same. So I can replace this by the domain, which is written there. And again, this has a specific name. It's called H2, but now with a 2 on the top of Rn. Does anybody know the name of this space? H2, but with, or HS, but H2 with an exponent 2. It's called the Sobolev space. The second, because it's with the power 2, second Sobolev space. Again, this is just the domain of the Laplacian, and it is the image by Fourier or Fourier inverse of the space there, but it's also the, oh, sorry, here there is a mistake. It's a domain of x squared. It is a domain of the operator x squared, sorry. And the domain of x squared is the same as the domain of this Japanese bracket power 2. And it is what I call H2, and the Fourier transform of this space is what people call the Sobolev space. So this is, again, a self-adjoint operator. This guy is self-adjoint. Right. Any question? So we have seen multiplication operator and differential operators. Why? Because you take derivative. And now, since I introduced before just xj, I have to introduce dj. So this is just for information. So dj is minus I xj. And probably in quantum mechanics, you are going to call this pj. There are different names for the same thing. So dj and the domain Fourier transform of the domain of xj, just multiplication by this variable is self-adjoint. I already mentioned it. Is self-adjoint. For any j from 1 up to n. And it has a name. This is called, one fourth year should know, third year, in quantum mechanics, it's called the momentum operator. Momentum operator. While xj is called the position operator. Well, in fact, you have a family because you have, so I should be a little bit more precise. The position operator is a family D1 up to Dn because we have n. So you can take momentum operators, and position operators is x1 up to xn. Now it's precise because you have n of them. And momentum operators and position operators. Exercise, which is completely standard. And everybody has to do this once, at least in this framework, on the Schwarz space. And I will tell you why on the Schwarz space. Check that these two operators, xj, xk, equal to 0, dj, dk. What is a commutator? Maybe I didn't introduce a commutator. Do you? Sorry. What is a commutator? The commutator of AB is AB minus BA. This is the definition of a commutator. It's called a commutator. Maybe I didn't introduce this. No, not in this. So now you know it. It's just AB minus BA. So check that xj, xk, they commute. dj, dk, they commute. What about dj, xk? Yeah, probably there is a minus I. You're right, minus, no, not just the I guess. Maybe it's only I. Modulo error, this is the operator 1 times Kronecker jk. So it means whenever it's j is different from k, it's 0. Whenever j is equal to k, it's the identity operator. Why on Schwarz space? Because look, when you write such a guy or two guys like this, it has to be meaningful. So if you take a f, if you apply this on a f everywhere, f has to be in the domain of the first one, and the image has to be in the domain of the second one for both. If you take an element in the Schwarz space, you can multiply by any polynomial, you're in the Schwarz space. If you take any derivative on a function in the Schwarz space, you are again in the Schwarz space. So the Schwarz space, you can do this computation. It turns out that you can take a domain which is slightly bigger. So you can go to a bigger domain, but already you can check this on the Schwarz space. And this is just a matter of writing what you have and maybe doing an integration by parts. Or maybe even, no, there is no integration by parts. Take a derivative, that's all. Because this is a very standard exercise. So two families of operators, multiplication operators, differential operators. Let's look at a third family very quickly. Convolution operators. No, probably you have not heard about them, but still in L2 of Rn. Of course, by the way, I'm giving these three examples in this Hilbert space. If you just take an arbitrary Hilbert space without specifying anything, you cannot say so much. On the other hand, if you want to consider L2 of Zn, we have seen that it is also a Hilbert space, then you can define other operators which appear naturally. So the family of operators depend on the Hilbert space. It's quite natural to consider L2 of Rn, but you can consider other Hilbert space. So I consider phi again from Rn to R. I take again R and not C because later on I want something self-adjoint. And we set phi of D. It's on purpose that I put a D, like this D here. What is the definition? I take Fourier adjoint phi of X Fourier. What is it? So when you apply this on F, I don't need to put it on the F, but let's assume that I apply this on the F. What you do, take the Fourier transform, multiply by the function phi, it's a multiplication operator, and take again Fourier transform. So you have to be careful. Why you have to be careful? Because any F in the Hilbert space will be in the Hilbert space. F is unitary. But when you multiply by phi, if phi is growing, you're not sure that you are still in the Hilbert space. So you may have a problem to take Fourier transform inverse. So it means, depending on phi, you have to give a domain. You have to define this on a certain domain. So what is the natural domain? Who can tell? Oh, there is a small clash of notation, sorry. There are 2D, which are not at all the same. This curly D is for the domain of phi of D, which is just a notation. This is a notation. Who can give me the domain of this one? Look at the definition. Look at the definition. Everything is in these two lines. Yeah, this should be the set of F such that look at the right. I don't know what is the left-hand side. So I look at the right-hand side. I need, sorry, the set of F in H such that Fourier transform of F is in the domain of phi of X. And we know this. I mean, this is easy. Again, it's an integral condition. But for the same reason as before, this is the set of, I don't even need it. This is F star of domain of, sorry, this is a curly D, D for domain, the curly D of phi of X. For the same reason as before. If FF is in the domain, apply Fourier inverse or adjoint, you get F is in the Fourier transform inverse of this one. So we have a definition for this domain. Yeah.
But this one is I delta GT, not one.
No, if I put an I here, no, it's.
No. You need to erase that I. Okay. It's fine.
Okay, check. There is maybe, I don't remember. I haven't done this for a long time. So what it was correct?
There should be no I. If there's I there, it would be 1 times 1. Sorry, I times identity times the register.
Okay, no matter. Check. If there is a problem, it's only an I, but I think it's correct now. Okay. Because be careful, my DJ is minus ID.
Okay, then there's no problem. I'm correct.
I define DJ as this guy.
Okay, my bad. That's my bad. Sorry.
No problem.
Then that is correct.
Okay, so we define a new operator. It's just a new operator by Fourier multiplication, Fourier inverse, and we have the domain. Now, I'm claiming that we have already seen such operator. So observation. Observation. In fact, it's a generalization of a differential operator. What is minus Laplacian? I'm claiming that this is just Fourier. In which order? This x squared Fourier. So now I'm just saying that I can take it on any function and not only the function x squared. And you can wonder why it's, oh, and by the way, so this is just an observation. But then what we have, this phi of d with the domain Fourier transform inverse of domain of phi of x, which is simple. This guy is again a self-adjoint operator. Is self-adjoint.
And this is Rn.
Sorry?
This is an element of Rn.
Which one?
The x there.
Here?
Yeah.
No, this is the operator of multiplication by the function x goes to x squared. So we have a new family of self-adjoint operators. Now you could wonder why they are called convolution operator. Maybe you remember at one point I mentioned convolution already. I will recall one formula. So can you, let's check how it acts. So by definition, this is f star phi of x f hat. F hat is just another notation for Fourier transform. And when probably it was in the chapter about distribution, I said a Fourier transform a product into a convolution. So look, this is a product of two functions. This is a function f hat times a function phi. And we take Fourier. So you can check this. It's an exercise, but it's already on the website. This is, it's equal to this, and I will recall the convolution, the definition of a convolution. So this is an exercise. This is an exercise. But I think somebody has already done it on the website. Let me just remind you what is the definition of convolution. And by the way, what is this? Is the inverse Fourier transform. So it's f star applied to f to phi. So with phi hat convolution with f evaluated at x is constant 1/2 pi n/2 integral phi of y f of x minus y dy. This is a definition of a convolution. So as you can see, this operator I have just defined with a Fourier transform acts as a convolution on F. So this is why we call it a convolution operator. So it means the Laplacian is a convolution operator. It's a very special convolution. Now, additional example, other example, and I will not say so much. I will just give two names. If you consider H, which is minus Laplacian plus x squared. So as you can see, this is the sum of two operators I have introduced, the Laplacian and x squared. This is called the harmonic oscillator. And if you do any quantum mechanics course, you will study these operators. The harmonic oscillator. Second example, H, it's also called H. It's minus Laplacian plus C 1 over X. C is just any real number. What is 1 over X? It's a multiplication operator by the function 1 over X, 1 over norm of X. But be careful. This is not bounded. This is not bounded. So you have a sum of two unbounded operators. By the way, it is the same here. This is an unbounded one. This is an unbounded one. So what you have to be careful on, this is called the Coulomb or hydrogen atom. Hydrogen atom. The constant C plays a role. You cannot take an arbitrary C. Let me just mention. But for these two examples, be careful, domain. Domain is important. So it means you need to give a suitable domain such that this operator is self-adjoint or has some good properties. So I introduced three types of operators, but you can play more. And of course, there exist other operators, but these two are things that we study usually in quantum mechanics. And hydrogen atom is just a description of an atom of hydrogen. Good. Any question? So at least now you know from some operators, you know some of them, and you can play a little bit. Be always careful about this question of domain, because if you're not careful, you can get some stupid answers. Last section, 3.8. Spectral theorem. We want to go up until this part. What is the spectral theorem? Is going to be the generalization of the diagonalization of Hermitian matrix. Oh, who has not taken linear algebra yet? Everybody knows what is a matrix. I didn't check this. Hermitian, yeah, it's too late. You can still live now, but it's too late. Hermitian matrix, it's a matrix which satisfies, let me call it M. M is equal to M star. In this case, the star is complex conjugate transpose. Okay. So we know that for such matrices, there exists a change of basis such that these matrices become diagonal. and you have the eigenvalues on the diagonal. So now I would like a generalization of this, because this is good for finite dimensional space, Cn, but of course it doesn't hold for general Hilbert spaces. So what is the generalization of this? And this is the content of the spectral theorem. I need one or two definitions before. Yeah, we should be able to finish. And spectral family. Probably this is new for most of you. A spectral family is a map or function E from R to, I don't know if I introduce this notation, but it's easy because we know what it is. The family of all projections. So family of all projections. I hope you remember what is a projection. We studied this 3 weeks ago. A projection, I call it P. P is in this P of H. If P is equal to P square is equal to P star, okay? So it's a map from this to this, satisfying 3 conditions. So it's from the real line, 3 conditions. Normally a function I should write like this, E at lambda, for some, I guess, historical reason. This is not exactly how we write it. It's E lambda, E mu. So the evaluation of your function at lambda times the evaluation at mu. This is just a notation. So it associates any number of projections. So this is just a product of 2 projections. It is E of the minimum between mu and lambda. So you choose if one is smaller than the other one, you keep only this one. If they are equal, no problem, because it's a square. Sorry? Just real numbers. Lambda and mu are just, okay, maybe you prefer this notation, but this is not the one we use. Do you prefer this notation? It's a function. E is a function taking value in the set of projections. So it means this is a projection, this is a projection. But as I said, we don't use this notation, we use the previous line. But it's the same. So this is the first property. Whenever you have a product of 2, it's the same as a projection on the minimum value. The second condition is that E of lambda is strongly made when epsilon goes to 0. What does it mean? It's a continuity condition. It means if you arrive from the right, you reach E lambda. I'm not claiming the same for the left. So it's called a right continuous function. So I will just draw what I mean on the real line. Oh, no, sorry. Make it here again. It's on purpose that I make it increasing, but it's not in the definition yet. Look, this is a function which is right continuous, because whenever you come from the right, you have the value at this point. I'm not claiming that it's left continuous. And the third condition is that limit when when lambda goes to minus infinity of E lambda 0, and the strong limit of E lambda when lambda goes to plus infinity is a 1 operator. So think about this. I'm going to do a slightly different picture, which is misleading, but it helps. You can think about a projection as we have seen as a kind of characteristic function. So the E of minus infinity would be just the projection on 0. Then let me draw E 1/4, which is projection on something bigger. Then E of 1. Then bigger one, E of 3. And let's say E of 25. And the projection on everything would be E infinity. This picture corresponds to what I have in mind, except the continuity. Look, whenever you have projection, a product of two projections would be the product of two characteristic functions. Then with this picture, you have indeed the projection on the smallest one. And E of minus infinity is just the operator 0. E of infinity is the projection on everything. The continuity is not visible, but if you have this image in mind, it's the same. And of course, we have seen that for operators, we have 3 types of convergence: the weak, the strong, and the uniform. I'm just using the strong one. So it's a family satisfying these 3 properties. Again, the notation is an accident. Any question? So spectral family is a function satisfying these conditions. Yeah?
Right. You come to that point, if you go more right, it's discontinuous, right?
Not always. So let me indeed make a remark. I'm not claiming anything about left continuity, so remark. What we call E minus 0, this is just a notation. It means a limit from the right. E minus 0, this is a strong limit as lambda goes to, as epsilon goes to 0 of E lambda minus epsilon. In general, I'm not claiming that in general it is different from E lambda in general. And indeed, if you look at E lambda minus 0, this is E lambda minus 0 here. This is another for lambda prime. This is, the value here. The value here is E lambda prime minus 0. And I'm not saying in my definition, I'm not saying anything about them. So for some points, of course, here, the value from the left and from the right correspond. But at the jumps, the point is at the jump, the value is after the jump. All right. And increasing, I said, I put this increasing because this is one way to think about this condition. And we have to, okay, it depends if it is strictly or not, but these are just words. This is a precise definition. Just a second remark. This is remark 1. Remark 2 is that the projections E lambda for any lambda in R, they commute. Can you see this? Can you see that they commute? Yes, take 2 of them, write this, it's a minimum, write in the other order, it's still the minimum. And the minimum is independent if you take the first one or the second one, or the second one or the first one. So they all commute. So it's a family of commuting projections. It's important, let me stress it. Family of commuting projections. And I told you a few weeks ago that if you take two arbitrary projections, they don't commute. They have no reason to commute, but this family, a spectral family, they commute. All right. I'm rushing because I can see the clock. Okay, what we do with this family? We are already happy. We have a family, but we can do something else. Definition. I define E of interval AB open on the left, close on the right. I give a definition. This is EB minus EA. So if you think about this picture again, what is it? It's a projection on a shell. This could be E3, E on the interval, sorry, it was E1. This could be the projection on E interval 1, 3. Any question? I give it as a definition. Yeah.
But that seems like R1 to me, and that seems like general Hilbert spacing. Like
yeah, this is just a picture there. No, this has not a precise meaning. I mean, the meaning is here, but I try to make it intuitive by making this picture. And then this is something I cannot then extend this definition to the set obtained by arbitrary, I will explain, by arbitrary intersection, no, not arbitrary, countable, by countable intersection. Intersection unions. Sets. I need this. Let me explain. I define it on a very specific interval. But of course, you can take any interval like this, take any intersection, take any union, take any complement, countable. So you end up with many, many different sets. And you can extend this definition. You start by taking two intersection, two union or complements and blah, 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 and you generate all sets of these types. And this has a name. So the set obtained by intersection, union, and complements of open or closed sets, you get the same if you start with open set, closed set, or set of this type. This has a name. It's called AB. It's called the Borel sets. I cannot spend too much time on this. I'm just saying, take the open set or open interval, or maybe I should write here open interval or closed intervals. So you take any open interval or any closed interval, generate intersection, union, so on, and you get what is called this. Essentially, the most general kind of subset of R. No, it's not the most general because we do it in a countable way. a Cantor set, you would do it in an uncountable way. So you don't reach Cantor set here. Okay. So what we end up with, and this is this. So we have a spectral family, I explain, because it's easier. And we end up with a spectral measure. So what is a spectral measure? It is a map. Again, I'm going to call it E. It's the same E from this set to the set of projection of H. Such that E of V1 union V2 is E of V1 plus E of V2 if V1 intersection V2. This is something you should expect to look at the picture I had done before. If you have two disjoint interval, this E of two disjoint interval is going to be first projection plus second projection. So what we have, we started with a family indexed by R. We end up with a function, and I keep on purpose the same notation, taking any set, not completely general, but almost any set of R in the set of projection. So the last sentence about this. And then I will tell you why I do this. There exists one-to-one correspondence between spectral families and spectral measures. Be careful, it's maybe one of the most important part of this lecture. If you understand what I'm going to talk about now, it's really good. So what I'm just saying is, if you have a spectral family, you can define by this construction a spectral measure, but the converse is also true. If you have a function from this set to P of H, the set of projection, you can easily construct the spectral family just by taking the interval minus infinity lambda. It's the same thing. It's just two things of different, two versions of the same thing. Okay. What I want to do with this. You remember 2 weeks ago, I spoke about function phi from an interval AB to B of H. It was an operator valued function. We are essentially in this framework. We have functions on R value in the set of projection, but a projection is a special case of a bounded operator. So we are going to come back to what we have seen at that time. And so I'm going to consider phi from AB to C. So I just take with value in C, but I define the following thing. Can you guess, who guess what is the meaning of this? I give you A or A plus if you guess the meaning of this notation. All the ingredients have been presented. It's a Riemann sum. It's a limit of a Riemann sum. Think about an integral. So you have an interval, AB. You have phi, I take it like this. And indeed, I can subdivide. Okay, I can subdivide. Now, each of these intervals, I can pick the value of phi at one point. If I make it small enough, it will not make a big difference. Time the projection corresponding to this interval. And we have in this family, we have this projection. So this can be written as Riemann sum. I'm a little bit fast, but if you have seen Riemann sum, you can guess it's going to be a sum, j from 1 up to capital M, phi at a point Cj. So this is interval xj minus 1 xj, and we have a Cj somewhere in between. Phi at a point Cj times E of this interval xj minus 1 xj, and do the sum. Of course, it's not completely trivial that you can take smaller and smaller interval, but if phi is nice, it's going to converge. So it's a lemma, but I just write it as a remark. If phi is continuous on AB, this Riemann sum converge in the strong sense when smaller intervals are considered. Again, it's a limit of operators, so you have to specify in which sense you take convergence. But so think about it. For every point, I take one complex number times a projection, and I multiply these two. So I take phi at Cj times this projection. And it turns out that if phi is a nice function, this Riemann sum converge in the strong sense. Sorry, I'm a little bit too fast. It means in the strong limit of this converge when smaller intervals are considered. This is a Riemann sum with operator valued functions. Okay, now let me, is there any question? Of course, it's very fast. Try to play with your hands and try to understand what is going on. Within 20 minutes, we cannot do much more than this. But at the end, I will state a precise theorem. So, proposition. Which is going to be useful. The interval of AB, phi of lambda, E d lambda. So this is a notation for this. We write integral AB of phi of lambda, E d lambda for the limit. And it's an operator. So this is just a notation, but it explains the limit of this. So here I should write a limit when n is going to infinity. In this sense, it would be more precise. It's an operator. I can take its norm. Do you have a question? Look, if phi is bounded, these values are always smaller than the maximum value. So this is going to be smaller or equal to norm of phi infinity. And I recall that this is a sup of phi of x for any x in AB. You shouldn't be surprised by this. Why? Because as I just mentioned, all these values are smaller. And remember, this family had the property that when we consider the biggest one, it was 1. So we just have 1 times the maximum value. So this is why we get this upper bound. So you shouldn't be too surprised by this. The second thing is, if I consider AB phi of lambda E d lambda, it's a bounded operator, so I can take its adjoint. Now, can you tell me what is this adjoint? Decompose it. Each projection is a projection, is self-adjoint. So the adjoint is just going to be the complex conjugation on the function. So this is the integral AB phi complex conjugate of lambda E d lambda. And what can you conclude from this? If phi is real valued, it's self-adjoint, right? One last property, which is I need slightly more space, which is a little bit counterintuitive, but it's correct. Let's see. Integral AB phi of lambda is E d lambda, and I multiply by another one. Integral AB psi of lambda E lambda. So I take 2 operators of this type. Can you guess the product? Decompose it into small sums. And remember, these interval, when you take 2 intervals which are disjoint, the product is 0. Think about it. The product on 2 intervals which are disjoint is 0. So it means if you write small sum, most of the product will cancel, and you will end up with integral AB, just the product of the 2 functions, E d lambda. The proof is because these many products will cancel. Okay, we are here. The spectral theorem is here, so almost the end. This is fine for AB finite. And as I said, we obtain bounded operators, but of course, this is too small. I want to deal with unbounded operators. So how to deal? So this was the end of the theorem, how to deal with A going to minus infinity, B going to plus infinity. And of course, I have to be careful because if it gives me an unbounded operator, what are you playing with? Okay. If we take A and B going to minus infinity and plus infinity, I will end up with an unbounded operator. So I need to give a domain. So let me, definition for any phi from R to C. I can start with C. We define integral on R phi of lambda E d lambda. But as I said, this cannot be defined on arbitrary vector because if phi is growing, you end up with an unbounded operator. So with domain, so what do I want to have? Okay, I need to maybe just one parenthesis before this. I skip it, but I probably need it. So please keep 3 lines here or 2 lines and write this observation. It could appear before. We will refer to this observation. For F belonging to H, consider the following thing. It takes one of these general intervals. So think just about an interval, send it to this E of V. So it's a projection applied to F, scalar product with F. And by the way, observe it's the same as E of V F square. Why? Because it's a projection. It's a projection. You can take the square and put it on the other side of the scalar product, and you get the adjoint, but the adjoint is the operator itself. It's a projection. So you get this. So it means this is always bigger or equal to 0. It's not a complex number. It's a real number, bigger or equal to 0. And one has this E of V F squared. I want an upper norm. Can you guess what it's smaller than? Sorry? No. Look, the biggest projection is, so it means it is smaller than, yes, the norm of F squared. For, you get it for V is the entire line. So you have a function. So we end up the map AB, take a V, goes to this E of V F F. So it's a function which take any of these intervals and send it to a real number, is what we called is a measure on R. So what is a measure? It's a way to measure the size of things. Indeed, you take any interval or general interval, you get a positive number or 0. And if you take 2 disjoint, no, it's no more, but I already mentioned, if you take 2 disjoint intervals, you get the sum of the 2 measures. This is exactly what we want for measure. But it's a bounded measure. It's not like the Lebesgue measure. The Lebesgue measure on R is infinity. It's a bounded measure because if you take the entire line, you get just this. So it's a bounded measure. Okay. And I'm going to give a name to it. This is why I mentioned this. I call it MF of B. M is usually for measure, F because everything is based on the F, and V because it gives me the size of this V. So now the claim is that the domain is of this operator with domain D phi. I call it D phi because it's based on a function phi. Is it the set of F in H such that integral of phi of lambda square MF of D lambda is finite. So what it means, think again about Riemann integral. You have a measure, so you are able to measure small interval. So you have a measure. It's an integral over R. This function, think about an example, the function x goes to x squared. You know that it's not integrable. But if f decay fast enough, this will be finite. So this is the game. You take this function which grow, so you take I, you subdivide into small interval. In each small interval, you take the value of this guy. You measure with this measure the size of this interval, and if this sum is finite, you keep the f. If it is infinite, you throw it away. I know it's very dense today, but theorem, this operator integral on R of phi of lambda E d lambda with the domain d phi I have just introduced is self-adjoint if phi is self-adjoint, if phi is real. So in a sense, for any spectral family or any spectral measure, it's the same. I've given a meaning to a self-adjoint operator for any phi. But one special function which we like is the simplest one. Take phi is equal to the identity function. What is the identity function? It's identity function of lambda with lambda, or the perfectly linear function. So you can apply this to, you can apply this statement to this special function, right? It's a special case. Now, what is the spectral theorem? Theorem. What is called the spectral theorem? For any self-adjoint operator A, domain of A, there exists a unique spectral family, but as I said, this is the same as saying this is the same as a unique spectral measure, because you can construct one from the other one. So this is just a parenthesis, such that, can you guess the end of the sentence? I have constructed self-adjoint operators. I'm starting with an arbitrary one. I want to say that all of them are of this form. So there exists a unique spectral family or spectral measure such that A is the integral on R of the identity. So I can write lambda E d lambda. And domain of A is nothing but the domain of the identity function I have just mentioned. So any self-adjoint operator can be written in this way with a domain given by this. And alternatively, but this was already written, if I give you a spectral family or spectral measure, you can construct an operator and it is self-adjoint. Why is it a generalization of the diagonalization of matrices? Because look, for any lambda, or close to any lambda, you need to discretize a line, you have a projection. So essentially, you can think about this as an infinite sum from 1 up to infinity of lambda. It's not correct, but E of it's not correct because usually this would be correct if the operator has only eigenvalues. So for any eigenvalues, you have really a projection. But in general, this is not a projection. In general, if it is not an eigenvalue, this is 0. But you can construct a small interval. And this is what we do with the Riemann sum. It's a small interval, but still it's a projection. So it's an up. This is true if the operator has only eigenvalues, but this is a general statement. So this one is true. This is correct if the spectrum of A is made of eigenvalues only. But in general, the spectrum of A is different from the point spectrum of A. And for the spectrum which is not an eigenvalue, you cannot write this, but we have given a meaning to this with this Riemann integral. And this is useful because if you study these kind of things, you are studying, in fact, the most general self-adjoint operators. So if you can say something about this spectral measure, it's the same as saying something about this self-adjoint operator. If you can say something about this domain, you are saying something about this domain, right? So any self-adjoint operator can be seen as, in a certain sense, a continuous limit of projection times a certain value. But this is only an approximation. And for this reason, usually we write here just A for this, we put an index A for the spectral measure because it's a unique spectral measure associated with a self-adjoint operator. Okay. And also, it's natural in this context. In this context, it is natural to write. Remember, just before I have introduced the general situation I've written this not only for the identity function, but for an arbitrary phi. How should you call this operator? If for the identity you get A for general phi, yeah, no, not A phi. It's natural to call it phi of A. And indeed, if you come back to what I introduced before for convolution and other things, it's exactly this. So it coincides. So it's a perfect match. This function of A corresponds to this. And you know some example, if phi is, for example, a polynomial, you would just get the polynomial of A, so you replace the variable by A. In the notes, I have added one more information. So look, we have a one-to-one correspondence between self-adjoint operator, spectral family, and spectral measure. So you can go from one to the other one. It's bijective. There is a fourth object it is unitary group. I will not explain, it is in the notes, but I will just write a formula, unitary group of the form EITA for T in real. You know, fix a T. This is a function. The function e power it is a variable, so it's one of the phi. I can define this. Now you check that if you change T, you get a certain family. It's called a unitary group. It's a representation of R. And the theorem, the longest version, says you have a one-to-one correspondence between self-adjoint operator, spectral family, spectral measure, and strongly continuous. To be perfect, I should write strongly continuous unitary group. So, and this is how you have some dynamical system in quantum mechanics. Any self-adjoint operator define a dynamic by this formula, and this is at the root of Schrödinger equation and so on. Right. So you have everything here. These four bijective things. That's it. Good luck for the future. You have now to apply this. Whatever you do, you have to use this in your quantum mechanics, in your economics course, in your chemistry course, in your engineering course, or whatever. So all these tools can be used in different frameworks. Thank you.